truss analysis. And then today we're going to start on the lecture of intelligence, which is a beam or fractal element. Okay? So in building a structure, okay, you know that not all structures are truss. Truss structure are brought with the pin support. But in the case of this overhang structure or even pillar, okay, you want it not on the pin support, you want it to be clamped fully to the ground. So in this case, so you're then going to have the beam element, even though the structure looks alike, but the beam element usually will undergo lateral bending. Okay? So you can see that truss is a network of bars that experience tension and compressions. So yeah, they have the end being the pin joint. Okay, on the other hand, the beam, okay, is the element that resists the bending. Okay, so like for example, let me draw. Okay, so you also have a, let's say a cantilever beam. Okay, this beam itself is going to support a weight of force at the end if this is a cantilever. On the other hand, if you're going to have the pin support, so this itself is a truss or is a bar. Okay, it cannot support any vertical loading. So you will do this, they will simply collapse down. Okay, because of the rotation about the pin support. Okay, so this is a big difference. One is the clamp support, the other one is the pin support. Okay, pin support will allow rotation, but the clamp support will not allow. Okay, so as a result, you can see this. The top one will have deformation, which is called a bending. Okay, it is a transverse bending. Okay, on the other hand, this one, if you want to pull it, you can only support a tension or even a compression. Any perpendicular force will not be resisted. Okay, so this is a big difference between a truss and beam element. Okay, so in the case of analysis, we will come out a beam element. Okay, so independent of the truss. So that will be useful for analysis of the frame structure. So in the end, you can do optimization, but let's show you the beam structure or sort of the frame structure. What you can see here is the frame structure, okay, are basically the combination of the two. So if you now want to make the frame, a bicycle frame, okay, so your bicycle frame, let's say I make a triangle, okay. Imagine if this is a crossbar, and this is your steering, this is your seat, okay. This can be treated as one whole body, but it's going to be supported by, okay, by weight, okay. This is your pedal, and this one will be supported on the rear wheel. And then here, okay, it got to be supported by the front wheel. You see from the loading point of view, okay, the weight of the drive is going to be divided by the front wheel and the rear wheel. Okay, it is equally. If it's not equally, then you're going to have the N1, N2, being the normal force. Okay. So imagine if your structure, okay, what makes the structure? Okay, for the real part, you can have these this triangle being a structure. Okay, if you look at your bicycle, the bicycle are welded. Even though if you want to use a pin support, that's fine. Any triangle will be a stable structure. So you can see that. Okay. But here mostly are welded. Once it's welded, it becomes a beam. Okay, and some more. What is the second triangle? That led the structure. Okay, the second triangle that you can see here is this. It's almost behaving like a truss. Okay, but definitely, okay, what makes the truss, okay, is your foldable bicycle. Okay, the front are foldable. But in the case when you want it to be solid, okay, these joints are all welded. Okay, all welded. Okay, they are not allowed to have rotation. But once you are subjected to loading, they could possibly have inward bending, okay, or outward bending. So one of the simplest this beam structure that you can imagine would be a bridge structure. Okay, a bridge that is supporting the middle weight. Then also have this transverse displacement. Okay. So in modeling, okay, this is a pure bending. Okay. When it's subjected to transverse loading. However, when you look at here, apparently this structure, as I mentioned to you, is going to support the weight. Okay? And this weight is going to apply along partially in the axis direction. So this is the axial direction. So in this case, then this element itself is then going to be modeled, okay, both as a truss because of the axial loading, as well as it can be modeled as the beam because of the transverse loading. Okay, so do you see that? The structure itself, whether it's a truss or it's a beam, it's not because of the construction, but because of the loading. Take for example, if I have a chuck here, okay, if I do the compression, it is a rod. If I do a pull, it's still a rod. But if I do a bend, okay, then it becomes a beam. Okay, and this structure is called a frame structure because it's a combination of truss, okay, plus the beam. Okay, so in later lecture we're going to have the NC hands-on sessions, okay, to try out the beam modeling. Okay, so of course to start simple, you can model. You can take the example of the wing as a cantilever. I think we showed this before. Yeah, let's play this video again. Okay. So what make the simplest cantilever? Okay, you can have this example. So this is a vibration test to find out what is the vibration frequency of the wing structure. The bottom was a center, that applied the linear force. The top was a cylinder. this flapping wing, then you can see more clearly. Let me show you one example. Okay, this is not a very striking illustration, but we'll show you the flapping wing illustrations. So imagine that if you have a flapping wing like this, okay, what would be the loading? Okay. So this is the wing that vibrate up and down. Definitely the loading on the wing, yeah, will be more substantial. And sometimes you can see the wing is actually rotatable. Okay. It's not first of its kind. Yeah, a similar design, a four-wing design, has been developed I think in the 70s or 80s. So this is the 8-wing design. In comparison, you can see a smaller, more flexible version. Let's see this smaller, more flexible version. Okay, this is in our lab. You can see that this is the wing and this is the leading edge. So supposedly this is the only beam structure. So during the course of this flapping, you can see the bending of the beam. When the wing is subjected to drag, the beam will start deflecting up and down. Okay, so you can see that for any lightweight structure, so the deflection could be quite substantial and observable. So this one, the video also will show you the actual speed of the flapping, and then at the lower speed, you can see that because of the reduced drag or inertia. Okay, this is actually the slowed down version. So the actual force is still there to deflect the leading edge. Okay, so not just the bending is not just applied to small aircraft, it also applies to a big aircraft in the strength test. Okay, as you see this before, I think we show this before. Then we straight away go to the bending.
Load the specimen mechanically and also to pressure and go to the extremes to check the structural behavior of the girl.
Yes, we showed this before. I think we just show here the bending of the wing structure.
Pull up the wing, pull downward, pull the fuselage in all the critical situation. Okay. We have installed 12,000 sensors on the specimen.
Okay.
So you can imagine between the offloading position of the wing, when we compensate simply the weight of the girl, and the max level of load, we have more than 5.2 meters displacement. So let's climb into the installation.
Okay, this kind of test is exaggerated, but it's necessary, especially during the flutter test. So let's show you the why you have to design for the worst situation. Let's see the video of the flutter, the NACA flutter video. Okay, let's see the resonance. Yeah, you see this NACA resonance test. Because during the flight, vortex will have shedding. So structure, especially lightweight structure, they will have twisting, bending, yeah. things, then we know that there is a need to consider the beam bending. Okay, what makes a simple beam? Okay, yeah, you can use your previous knowledge. Okay, from mechanics of material to study that. Okay, this beam bending theory is not just happen to a big structure. It happens also to the some bimetal. So when you have the bimetallic strip, when you are doing the heating, then you will do the unbending. Okay. So the bending of bimetal strip happens because of the differential expansions, and that difference in the axial elongations will be converted into bending. Okay. So that's why again this structure should be considered as this frame structure. It's a combination of bending as well as the axial expansion. The next example I'm going to show you. Okay, in this case, if you have the rod expanding, it is possible to have elongation and then it result in rotation. This happens in the case of your on the pin support and some movable pin, then you could possibly relate the elongations due to thermal expansions to this vertical displacement. Okay. So this kind of structure is there. Okay. On the wafer. So you see this kind of structure under the microscope. So the beam is there. It's a long beam, but it's a chevron or V-shaped beam. So under high magnifications observation, you can see the beam elongating and then moving vertically. This is all fabricated on a silicon wafer. You amplify the tip stroke by using a dial. Then you can see that the vertical displacement indicated as the angular change. Okay. There are many examples of the beam structure. Okay. Then let's come to the mechanics of beam bending. In the case of beam bending, you're basically having multiple layers being bundled together. Okay, imagine if now I only have one layer like this. Okay, I can do simple bending. But now if I have two layers, okay, one top, one bottom. Okay, if I do the bending, so you can see the edges. Without any covering, the edges will slide over the other edges. So this is the case of separate layer. If you now do the covering of the layer all along and you start doing the bending, you will find that the top layer, okay, is going to undergo a tension. And then the bottom layer is then going to undergo the compression. See clearly? Okay? Okay, this might not be clear enough. Okay? The one under the compression, okay? Yeah. It is separated, it will be buckled. Okay. So let's analyze the structure. Okay. Yeah, so this part, let me try to draw it out so that you have a clear idea. The first thing we're going to analyze is quite a straightforward one. If you have the beam and if you subject it to a pure bending, okay, this beam will have a starting length of L. Okay, and if you bend it, okay, let's say this is the neutral plane. Okay. We'll still have the starting length of L. So this is the neutral axis of neutral plane. Okay. However, you know it clearly. If something from the geometry of an circular arc, the radius. And this must be the arc. The arc length is equal to radius times the angle. Okay? So by doing so, you can do the calculation. Okay, the top layer, okay, which is away from the neutral axis by a height y, okay, will then have a larger radius. Okay, this is r plus y. So as a result, this line, the line which is on the top, will have a value of r plus y and theta. So as a result, what's the length change? Is L prime minus L is equal to r plus y minus r theta. So in this case, you can see that this is the length. Okay? The length change is equal to the height and the angle. And what is your angle? Accordingly, your angle can be determined from the something length divided by the radius. So here you can say delta L, okay, is equal to what? Equal to y L over r. Okay, if you now do the re-expressions, the length change over the starting length is equal to y divided by the radius. So this is what you have for the strength. You have the strength. Okay, the strength is equal to delta L over L is equal to y over r. How about your stress? The stress is young modulus times the strain. Okay, how much is the total moment that is required to bend this? Okay, since over the sections, okay, you can see this is in tensile strain, and this one is in compression. Likewise, the stress also, tension, and then this is the compressive strain. Okay, so to find out what is the total moment, okay, take this tension force times the y. Okay. So this tension force, small df times y is equal to the stress times the small height. Okay? And then this is equal to what? Equal to your y squared over r and then e and then dy. Okay? So this is your small moment required to do the bending. Okay? This is a small moment required to do the bending. If you now do the integration of a small moment, then you're going to have your e and then y squared. Okay, because of the common radius here, take the radius out and then this dy. Okay? So the total moment required to do this bending is this expression. Okay, I think I forget to find out the area. The area will be the width. Okay, the area will be the width. Let's say v. Okay, v and v and times v. Okay, so as a result of these expressions, if you go to do the integration from t equal to y equal to minus d half to y equal to e over 2, and then this is y squared dy. So this expression can be written as y cubed divided by 3, and then this is d over 2 negative, this is d over 2 cos d. So in the end, you have e to the power of 3 divided by 12 over r. This is what we call ei, fractional rigidity, divided by the radius. Okay, so this is what you have commonly for the beam bending theory. Okay, so in the mechanics of material, you know this very well. Ei over r is equal to moment. Okay, but the mechanics of material, you don't write this way. You write this ei second order derivative of the this diffraction gradient, second order diffraction gradient equal to moment. Okay, what is this? This is 1 over r, the second order derivative of the diffraction with respect to the displacement. Okay. We have gone through with you what is the beam bending theory in these revisions. Okay, so this we have derived this the first equation, and the stress equation also can be determined. Okay. For pure bending, straight beam will become a curve. Okay, so this curve can be described using a circular arc. Okay, and it can be described using radius times the angle. Okay, if you now take this arc length, okay, you can find this arc length is the angle chain times the radius, but the arc length can also be described from the gradient. In this case, you move forward by dx and move down by dy or dv. Okay, so if you are using Pythagoras theorem, you can find that the arc length can be described as the horizontal displacement between the horizontal distance between the 2 points and the square root of 1 plus the gradient square. Okay? So the deflected angle, if you go and check this deflected angle, there is the gradient chain, that is dv dx. Okay? And the angular chain will then be the second order derivative of the vertical displacement. Okay? So in this way, how to find the radius? Okay? So this radius, inverse of the radius is d theta ds. That is the angular chain, small angle divided by the small arc length. That can be expressed as your second order derivative of the curve, okay, times dx divided by dx over the square root of 1 plus the gradient square. In the case where the gradient is small, so this is inverse of the radius curvature, okay, can be expressed as the second order derivative of the vertical displacement. Okay. So here there is a distinction here to let you know a beam will have greater stiffness, okay, when they are bonded together. The beam were not bonded together will have reduced fractional rigidity. Okay. So here's a quick check. Okay, these are two-layer beam. bonded together. These are two layers not bonded. Okay, if they have the same height or same cross-sectional area, what's the stiffness difference when they are subjected to same central loading? Okay, we'll have a quick check. Okay, how about yeah, behind. Neither did I. Which one is stiffer? First. Okay, the top one is stiffer. Okay, simple question. Huh? Okay, then stiffer by how much? Sau面有印，底下面印类。So this is stiffer. The top one is stiffer. Stiffer by how much? Any quick answer?
You are asking which one is stiffer, right?
This one already sure to be stiffer. Yeah, the top one is stiffer. Stiffer by how many times? Chỉ cần ta experience China. Okay, he said it is double stiffer. Okay, there is one possibility. Okay, how about it? Is it okay? Is it double? Double stiffer. So I just go through with you the formula. Okay. What's the rigidity? Okay. If I'm talking about the, okay, how do you calculate the rigidity? EI, okay, over R is equal to the moment, okay? So you can see here, this definitely the fractional list, okay. If you're going to do the integration, okay, then you have dI, dW, dx equal to the integration of n dx. Okay. Given the same loading, how much the angle change? If this is the same loading, I must look at my fractional rigidity. Given the same material, there are no difference in the E, but the difference is what? The difference is the I. Okay? This is one whole piece. My I is the integration of y squared dy starting from half thickness. Okay, so you can see what's your I. Your I is b y cubed. Okay, by substituting y12 and y12, this is then, what's that? This is the t to the power of 3, t cubed divided by 8, and then minus t cubed divided by 8. So this is b t cubed divided by 12. If this is the bonded layer. Okay? On the other hand, how about the bottom one? Okay, bottom one are two separate pieces. Okay? The neutral axis are different. If you want to do the integration with respect to this previous neutral axis, okay, what are we going to do? Okay, we're going to do the same expressions. Your I on the top, I1, and this I on the bottom, I2, can be expressed separately. Okay? If you don't bother about the midline, okay? If these are very close, then you don't bother. Then you just do the integration of y squared dy, okay, from y equal to 0 to y equal to half over 2. What are we going to have? Okay, you're going to have b, and then what's this? This is your y cube divided by 3 by doing the substitution. Okay. So this might appear no difference. Okay. From the just now derivation. Okay. But the real thing here is your integration here should be with respect to the midline. Okay, if it is with respect to the midline, then your expression, what I'm going to do, you are going to write something as y plus thickness over 4. Okay? No, I'm going to do that. No. Okay. Then we can take the offset. Okay. Let's use the para-axis theorem instead. Okay. So you can take integrating above the top and integrating below. Then you have your y prime. So starting from e over 4. E over 4. Okay, you have that. Okay. Okay, you can do this integration. I think it's more complex, but in general, okay, because of the thinning, okay, let me see. Okay, if I'm doing this by neglecting the top, then if I write it now, okay, okay, this one is very thin. So if I do the expansion out, y squared plus 2y e over 4 plus t squared over 16. Okay? Yeah, there are many things to integrate, but if I take the one which has the larger value for integration, I just show you by doing these integrations. This is starting from your e over 4. Then you have b over q, and this time around you're going to have y cube. This is a t cube. 4 times 4 is 14, and then times 4 again is 64, and then this one minus t cube over 64. So as a result, what you have, if I'm looking at the first term, this first term going to have the b over 3, and then this one is b thickness over 32. Okay? If now I take the first, this is I1. Okay, if I now take I2, okay, to the other integral, okay, this is going to be bt squared over 48. Okay? So the difference is what? The difference with comparison to that one is 4 times. Okay? 4 times. Yeah. This is negating the parts behind. Okay, if you want to do more exact comparison, you have to add the parts behind. Okay, so as a result, it is not half, it's at least 4 times difference. Okay, so this is the difference. Okay, so if you want to go for a more flexible structure, yeah, you can release the bonding. Okay, yeah, but if you want a stronger structure, the pieces should be bonded. Okay, so this is important also for aircraft structure. You look at aircraft structure, all the aircraft structure are riveted. They have the skin, inside, outside, middle by the honeycomb, and then the riveted the layer together. Okay, then you have the structure. Once riveted, means it is joined together. Even though there may not be a common structure that is bonded throughout, but because of the very short distance riveting, then you can make them a more integrated multiple layer. Okay. And then next, yeah, we already described how the strength will be described. The strength is proportional to the distance away from the neutral axis. As you can see here, the strength is the difference. If the bending was curling up, the top one will be undergo the compressions. Yeah. And then stress can be expressed as a Young modulus times the strain. And now if you now do integration of the stress times the area and then times the height away from the neutral axis, then you got the bending moment about the neutral axis. And then after the integration, then you got the expression here. So in short, okay, then in summary, you can get these expressions. Okay, so next, after you have the expression then, okay, then you can use this to calculate the bending. Okay, previous case was considering pure bending, but in the practical applications, the beam is subjected to distributed loading. Take for example the wing. Okay, the wing are subjected to drag or lift, so there are no pure moment on the two ends. Okay, but the loading is all along. Okay, as a result of the distributed loading, if you do the integration of the load along the length, then they must be equal to certain force. This force must be overcome by the shear force on the cut of the two ends. Okay, so if you take the cut on the right end, you have upward shear force positive, then you have negative or downward shear force B on the other end. Likewise, you can do the moment sum, because this is the thing. Once you make the cut, you have to replace it by the shear force and the moment. Let the moment will be clockwise on the left hand side, counterclockwise positive will be on the right hand side. This is how you define your beam bending. Okay, now we're going to do the force balance. The force balance in the vertical directions will have the upward vertical force B plus BP minus the this is downward positive. If it's downward positive like that, then you're going to have the expressions in this way. But later I think this is what you did for the mechanics of material. But later in the final element, we'll stick to upward positive rather than the mechanics one. So this is the negative. Yep. And then next, then you have the moment sum. Okay, the moment sum about the second point. Okay, you are going to have zero contribution of the shear force to the moment, and then moment on the right hand, m plus dm, going to be subtracted away by the m on the other side, and then this vertical force is also contributing to a moment, but it must be the distributed loading and the dx and the moment arm, which is half the distance. So as a result, we're going to have the expression the dm dx is equal to v. Okay. So let's take the example of cantilever beam. So in the case of cantilever beam, okay, this is a cantilever beam of full length L and is subjected to tip loading of force F downward. Okay? Let's find the moment at the distance x away from the tip. Okay? So if you make a cut there, okay, x from the prime end, x prime from the free end. So now you can see that once I make a cut at x prime, okay, then you're going to replace the cut by the bending moment M and shear force B. Okay? So let's take the conventions traditionally used for mechanics of material. So a Smalling curve will corresponding to a positive moment. Okay? So this is a convention that takes account of the zero moment sum. Okay? Likewise, and then this Smalling curve will have the shear force on the right hand side pointed down and the shear force on the left hand side pointed up. Okay? On the other hand, if you have a pop-up curve, okay, the moment is counterclockwise on the left hand side and clockwise on the right hand side, and then the shear force on the right hand side is upward and shear force on the left hand side is downward. This is a convention for mechanics of material. Okay? Okay. But in our case here, let's take some convention. In the formulation of finite element, what we stick to is displacement upward is positive. Okay? So no matter what kind of curve you have, left hand with the vertical displacement V1, yeah, right hand also has vertical displacement V2, they are all upward. Okay? But even the bending, we also stick to the consistent convention. Any moment counterclockwise to be positive. On the left hand, not one. On the right hand, not two. It's all counterclockwise positive. Okay? So we don't want to go for the way of mechanics of material. So you learned this before. Yeah, well, yeah, analysis, right hand, left hand. I know this convention is good. Why is it good? It's good to write the balance of moment. It's good to write the balance of shear force. But it's not good to do the count. Okay? So for finite element, you're going to develop a software to do the calculation. I don't bother your left hand and right hand. Okay? I want to stick to one convention. All displacement is vertically upward positive. All bending angle is counterclockwise positive. That's it. Okay?
Always positive.
Yeah. But then your formula got changed. Okay? Your convention for finite element is different from the convention of beam bending theory. Okay? But we can do consistently. Okay? So let's come back to the formula here. Okay? We learned about the governing equation. The moment is equal to EI over R. Okay? R is the radius of curvature. Okay? And then this can be expressed as EI second order derivative of the vertical displacement with respect to the length. Okay? And then the shear force, we also know that. Okay? How to do this shear force? According to our this theory before, okay? Shear force is the NEX, okay? Yeah. So, and then how about the distributed force? distributed force, as we derive from the beam bending theory, the distributed force is dV dx. Okay? So here, yeah, they already have the chain of convention, okay? So depending on what you take to be positive, okay? Okay? So the dV dx here, okay? Let's see here. Okay, let me draw this out. So this is taking the this convention, okay? And then if you are standing here, okay, to take the moment start, that's not true. Then this one is n plus dn, okay, minus n, okay. It's already taking the convention of counterclockwise positive moment, okay, or not 2. Okay, and some more, if you have distributed loading, okay, this is upward, okay. So this is the amount of the force is passing through the center, which is the distance dx over 2 away. So this amount of the force is q dx. Okay. Since you're standing at n2, so this one is clockwise. So the amount of the moment due to this is q dx times what do I have? Times the dx. Is it dx over 2? Yeah. Oh, okay. Yeah, this one. So then, if you now make it 0, then your dm is equal to q dx over 2. Okay? And this one to the other side. dm dx is q dx over 2. Okay? But not to forget, okay, this is only one part. Okay, I think this part is not the main one because second order of dx is going to be minor. The other big part there is your shear force. Okay, your shear force. This is upward. B. This one is downward B. The other part that we just now forget to do is this is your negative dx. Okay? So if you do the comparison, then your dm dx is equal to your b, and then minus q dx2. So this is a minor. Okay? So this is how you derive. This equation is right. And how about this top equation? Why we got the negative sign there? Okay. Okay, I think not to be corrected here because you are taking. Okay, then depending how you define the b. Okay, let me take the positive one. So you can now take the positive one. That change direction. Let's change this. Then I will add Yeah, even if I change this, formula is still there. This. Even if I change there, it's still positive. Okay, let me see. Yeah, where do I get the negative side there? Okay. Okay, this is right. This one, yeah, I think we got double check where we make this. Yeah, we'll come back to this point later. Okay. Okay, now let's come to the differentiation of the expression. Q is EI fourth order derivative of vertical displacement. Okay. Now we come to the important formulation of finite element. We assume no transverse loading. Okay. So you can see that in the actual loading, you could have upward distributed force. But in the case of finite element, if you take this out, okay, you take this out, this becomes a beam element subjected to shear force B. Okay, but no vertical loading. Okay. Yeah. So you can see that finite element cannot be precise. Okay, as compared to your beam bending theory. Okay, you are only doing the fine measures. Okay, by removing the distributed loading. Okay, so this is the first assumption we have. So you have to realize the consequence. If you take one beam element to do the modeling, okay, sorry, you better go back to the mechanics of material. That's more precise. Okay, because they have already removed the distributed loading. And then second, okay, because now you find out this fourth order derivative is equal to 0. Okay. Then what you can do? You can do integrations once, twice, third, and fourth. Then you can have distributed displacement as a cubic function of space. Okay, so that should be quite a straightforward one from the calculus or integral point of view. Let's move this up. Okay, what we're going to do is the fourth order derivative of B is equal to 0. So the third order derivative, okay, will then be what? Right. Okay, anyway, let's go back to this expression here. Yeah, you want it to be x1 first integration. A1x plus A2. A1x squared divided by 2 plus A2x plus A3. And then after the integration from 4 times, the third displacement equal to A1 x cubed divided by 6 plus A2x squared divided by 2, and then plus A3x plus A4. Okay? So now come to the point of the boundary condition or boundary value. In the case of finite element, you want everything unknown to be defined as something known or to be something solved. Okay, you could possibly have B1 on the left hand, B2 on the right hand, and then your theta 1 on the left hand, theta 2 on the right hand. So this is like you now have 4 variables and you have 4 boundary conditions. Okay? First, by substituting at x equal to 0, okay, what are you going to have? You're going to have your b is equal to b1 is equal to a4. Okay? Because x is equal to 0. The rest of the term all 0. And then next, dv dx theta 1 is equal to a3. Okay? And then lastly, then you apply the second boundary, okay, on the right hand, then x equal to l. Okay, then this expression here is equal to b2 is equal to a1l cubed divided by 6 plus a2l squared divided by 2. Your a3 has been solved as theta 1l. Your a4 is solved as b1. Okay, how about the dv dx? The theta 2 is equal to your a1 l squared divided by 2 plus a2. Your a, what's your a2? Yeah, your a2 is still not solved. Huh? A2 l plus a3. A3 is the theta 1. So with this, you're going to solve your A1, A2. Okay. So what you can do is you're going to re-express the equation. Move this to the other side. Then you can write unknown A1, A2, L3 over 6, and L3 over 2, L3 over 2, and then L. On the right hand side, we have the B2 minus B1 minus theta 1 L. And then your second row is theta 2 minus theta 1. Okay? So in this way, you'll be able to solve for your unknown coefficient A1 and A2. by the boundary condition, both the vertical displacement and the angle of deflection, yeah, you're able to solve all these. And eventually, you can find your A2 is equal to 1 over L times theta 2 minus 2 times theta 1 minus 3 over L squared times V1 minus V2. And then the A1 is the two angle sum divided by the L squared plus the two displacement difference divided by L3 times 2. Okay? So this is how you got this solved. Okay? Okay, once solved for the conditions A1, A2, A3, A4, okay, then you do the substitution back. Okay? You can find that Vx, okay, is the cubic function plus quadratic function plus the linear power plus the constant. Okay, but now, as for the finite element, we care about the shape function times the boundary. Okay, so the first shape function associated with vertical displacement is this expression V1 times the first shape function, and then this is the angle times the second shape function plus V2 times the third shape function, and then the angle theta 2 times the fourth shape function. Okay, so it might look a bit complex. What does it mean, the shape function? Okay. Okay, then we have a simple example. What's the shape function? Let's forget about the equation. Let's come back to the shape. This piece is a flexure. Okay, I have right end, I have left end. If I now move fix my left end, then I have my right end moving up. Okay, with the zero diffraction angle. Okay, so what's the shape function? You see, first shape function. Okay, if you're not sure, please get a piece of paper. Plan the left hand. Okay, plan the right hand, but lift up the right hand. What kind of shape function? This is it. Okay, yeah, the one. Yeah, without even an equation, you already have shape function. Okay, how about the second, the shape function theta 3? The theta 3, the n3 is I have my right hand fixed, no rotation, no vertical displacement, but I have my left hand fixed in angle, but elevated. Even not elevated. What's the shape function? You see that? This is exactly the second shape function. Okay? Yeah, it's easy to see the shape function for vertical displacement. And then next, what about the shape function of unit angle on the right hand? Okay, this is my right hand. Huh? My right hand does not move vertical. My left hand also no move. Some of my left hand is planned to fix the angle to be 0. I now turn my right hand for unit angle. What is unit angle? In radian. What's the angle in degree? If it is 1 radian.
Around 53.
You double check. Is it 53? Okay. Pi.
With 5.
No, 1 radian is equal to how many degree? Okay.
Iranian or just
1 radian. Okay. divided by 3 times 180 degree. About there, like that, about 60 degree. If I turn my right hand side, 60 degree. Okay, what's the shape function? You see that? The shape function 2 is by turning the angle by 1 radian. Okay? So this is my shape function. Okay? Theta 2, N2. How about the N4? N4 also, right hand is all fixed, 0 displacement, 0 angle, but now my left hand does not move up, so 0 vertical displacement, but I turn this 1 radian. Okay? Oh, counterclockwise. So then, okay, but the difference here is counterclockwise, I got to come down. Okay? This is counterclockwise. Okay? Not the same counterclockwise on the right hand. If I turn it upward, this is clockwise. Okay, me. Okay, clockwise. So in this way, you know the meaning of the shape function. Even though the derivations could be quite tedious, but the physics is very simple. Just get one piece of paper, lift it up, down, and then bend it up. Okay, bend it down. Okay, my right hand should bend it clockwise. My left hand bend it counterclockwise. Okay, but on your side, yeah, it's all clockwise, positive. Okay, the derivation could be complex. Okay, but after the grouping, the shape of the simple beam element is only defined by the vertical displacement on the right hand side, vertical displacement on the left hand side, the angle of rotations on the right hand side, the angle of rotation on the left hand side. So in this way, how much of the inference, how much the shape function? The shape function must be equal to 1 when you want to substitute in the local nodes. Okay. N1, N2 is equal to 1 when x is equal to 0, is it? No. N2 is not 0. Yeah. N1 is 1 when x is equal to 0. Okay? But this N2, okay, the inference is all 0, 1. Okay, you can see that. And then next, N3 must be equal to 1 when you substitute the x equal to n. Okay? Okay? So these are the shape function we said, okay? N2 is 0 even x is equal to 0. But the important thing of N2 being the one associated with angle must be 1 when you differentiate it. The N2 dx is 1 when x equals to 0. Okay? Because these two associations, okay, is only non-zero when you take dv dx. Okay. And then likewise, N3 is vertical displacement. It is 1 when x equals to L. Okay. But N4 is 1 and x equal to L when you take the gradient dv dx equal to theta 2. Okay. concept about shape functions and boundary value. Okay? Finite element are the ones that satisfy the boundary conditions. Okay? Anything in between is just an approximation. Okay? So that's why when you have a coarse mesh, your model is not accurate. But once you have the mesh refined, that should fulfill the boundary. Okay? So these are the shape function, okay, for vertical displacement. This is the shape function on the angle on the left hand side. This is the shape function on the vertical displacement at the right end. And this is the shape function for the angle on the right end. Okay? As such, you can write your vertical displacement at any point, okay, to be 4 shape function times the 4 boundary. Okay. Okay. If you are not sure what we are doing here, let me copy this. Okay, what we have right here is we are having the shape function multiplied with the boundary value. For each step, what do we do? For each step, we are doing the space derivations. This one. The second order derivative. And the last one, we're doing this third order derivative. Okay, by doing so, in here you got different expression of x multiplied with the boundary value. Okay, and then now, okay, we have a task. Okay, what's the task here? The task here is we're going to apply the derivative of displacement into the formulas that calculate the shear force. Okay? Okay, remember just now we did the beam bending theory. Okay, this time around, okay, I rewrite the beam again to stick to our convention. So I don't care about my beam mechanical material. I only care about stick to the FEM convention. Okay, let's take the moment sum going to be n plus dn minus n, and then this one is positive. So this is negative b dx. Okay. Okay, get here. Your dn dx is equal to b. Okay. So see how important your definition is of your symbol. Okay. My convention is nothing to do with mechanics of material now. I just stick to anything counterclockwise positive. I get the correct expression. And then next, how about your this the shear one? Okay. Shear force one, let's see. Okay, previously I have the Q here. Okay. Shear force one, vertical force, okay, sum 0. Then I have my, okay, this is a bit troublesome. It is the, yeah, it cannot be, yeah, it's up to your choice. Okay, it cannot be all positive here. Okay, they can't cancel out each other. Okay, so you still need to take the conventions. Okay, let's say the B, yeah, yeah, this one is downward, negative B plus B. Okay, let's see one section up or down. Yeah, you take this to be negative. Okay. Okay. Then you have the expressions. dV dx is equal to qx. Okay. So our convention here is something like this. Okay. That's why when you apply your this expression here, okay, because dn dx is equal to b. In the case when you have this side 0, when you got the expression there, okay, what is your b? Your b, according to the previous formula, is third order derivative of b. Okay, so this is the one that we're going to apply to find out the force F1. Okay. Force F1 is the force on my left hand side of the element, F1. Vertically upward, it is EI times the third order derivative of vertical displacement. It is obtained as these expressions. Okay? Where you got this expression? You got this expression from the third order derivative. Okay? Do that substitution. Okay? This first vertical force upward on the left hand side, and then next, how about the vertical force on the left hand side? Okay, you see why it's negative? Look at my convention here. My left hand force is upward positive. My vertical shear force on the right hand side is downward positive. See it? So everything depends on the convention you first from. Okay, of course, Big Bang theory should be there. You have one convention, but in the case of deriving or finite element simulations, your convention is this. So let me draw them out. Yeah. That is for the case of force balance, you got to write them. Okay? F2 is minus V. Okay? Why is it minus V? The shear force here is downward to fulfill the condition. But I define my vertical force to be F2. So isn't that it should be minus? Yeah. Your F2 is upward, which is opposite to your this free body force diagram. Okay? So as a result, you're going to have these expressions. Okay? So again, the third order derivative will appear to be on the right hand side, which is going to be negative. Now let's look at the moment. Yep. The moment here. Yeah, the moment here. Okay. Again, I think you got to choose the convention. This one to fulfill it. Okay, in order to make it is it the balance? Yeah. For the big value conventions, you want to choose it to be balanced. Okay. On the left hand side, the moment is minus. Okay. Minus n. So it's a minus EI times the second order derivative of the vertical displacement. Okay. And that second moment, that second order derivative is expressed as this function. And then on the right hand side, you choose this to be positive. Okay. So this is going to be the expressions. Yeah, the convention. Okay. Yeah, usually without the drawing, you wouldn't be able to define it that is. Next slide. Okay. So once you have that convention taken, you have all the forces, F1, M1, F2, M2. Now you write the forces, F1, M1, F2, M2. They are all function of boundary value. Okay? I have 4 equations in terms of force and moment, but they are all expressed in terms of the boundary value. Okay? So let's see how you do this organization. Okay, I take this example. The first equation can be written as the entry of the first row of the matrix. Okay. So please fill up the blank in the second row, third row, and fourth row. So after finishing the entry, now you've got your formulation of the finite element for B. Okay? So what you're writing here is the force on the left hand side, vertical force, and the moment on the left node can be expressed in terms of a function of boundary value B1, theta 1, B2, theta 2. Okay? Likewise, these force on the right node, node 2, as well as the moment on the node 2, can be expressed as a function of the boundary value, but the coefficient is opposite. So you can see here, is this element balanced? Yes. Why? F1y plus F2y is 0. When you do the checking, you do the sum of these two rows. They are cancel each other. Next is the force, is the moments balance in the element. Yes. M1 plus M2, you go and check. Yeah, not really, you can see that. Is you got to minus a 2 with it. Go and check this. Is it the right formula? Okay, let's check the diagonal. I think go and check. I think something is it right or wrong here? Let's see here. Your entry 6, 6, 2, 2. Okay, 6, 6, 2, 2. Okay, they are actually symmetry along the diagonal line. Okay, 2, 2. That's right. That's right. That's right. Okay. These two rows, they don't sum to be 0. Okay, moment 1 and moment 2 don't sum to be 0. Okay, they are net moment when you are subjected to certain load. Okay, but let's check what we learned. So the first thing we're going to do the validation is finite element formulations should reduce to a simple cantilever beam theory. Okay, what makes a simple cantilever beam? The left node, the right node, which is node 1, will have 0 vertical displacement and 0 angle of diffraction. And then next, when you subject the right free tips to downward vertical force F and 0 moment, what will be the answer of finite element for V2